electronics, converter-based resources, generators, etc. What do those do? They basically are finicky gadgets. What do I mean by finicky? They go sub-millisecond, sub-tens of milliseconds. And when you get there, they mess the grid up. So you have 5 panelists here, and the way they are structured is the first 2 people, Shahil and Brett, they are going to speak about look within the cycle, EMT, electromagnetic transients. The next 2 are going to look macro cycle, which is positive sequence, phasor domains, and subsynchronous responses and write-throughs. That will be Jin and Parag. The last person, that's Rahul, he'll speak from the load side, the data center side. Okay, so you guys have done all this modeling. What are we going to do? So that's pretty much your panel set up there. Before I hand it over to the panel, I'm going to give you guys a practical sense of why the modeling work these guys are doing is so important. I'm holding my laptop power adapter in my hand, and don't do what I'm going to do just now, okay? What I would suggest is to understand what these guys are going to do, are modeling, plug this end first into your laptop, take the power outlet end to your power outlet. So I'm saying connect the load first, then connect the source, and then go and jiggle the source. Has anybody tried what happens to the laptop? You will fry your laptop. Now, to put that in perspective of data centers, think of about 100,000 laptops put in a hall and jerked around by a thunderstorm. Data centers are going to protect that resource, no matter what. They don't want to fry the compute. This panel here is going to tell you what are they doing to model so both ends behave and get back to synchronicity. With that, I hand over. Over to you.
Thank you, Ashok. Hi, everyone. My name is Shahil Shah. I'm a power systems engineer at the National Laboratory of Rockies here in Colorado, formerly known as NREL. I'm going to talk about EMT modeling of data center power systems for evaluating particularly converter-driven stability issues and control interactions and oscillations. My colleague from PNNL will talk about more on the last signal transients in the presentation after this. So I want to focus on 3 topics. And the first is the factors that we need to consider during EMT modeling of data centers, like what is the architecture of data center, what type of power converters are used in data centers, and what are their operation modes. And the second, the types of converter-driven interactions in data centers, which can lead to oscillations. And the last, I'll talk about EMT PSPD model of an IT rack that we have been developing at the lab, and that we are going to release soon in a couple of months. So before I go into the EMT modeling, just want to set a stage of how a data center looks like. And if you look at this picture of a horizontal data center in Arizona, particularly for grid-connected data centers, there are some substation transformers which reduce the voltage from transmission level to medium voltage. And then they supply to these data center buildings. At each building, there are series of a bunch of medium voltage pad-mounted transformers, and as well as diesel genset as a backup, as a long-term backup. And then we take that medium voltage power, or which will be stepped down to low voltage by this medium voltage transformer inside the data center rooms, where the compute loads and cooling loads and UPS, they are located. So if I take you inside in an electrical schematic diagram, this is how it looks like. There are substation transformers, medium voltage transformers, and then low voltage UPS. The primary function of low voltage UPS is to provide short-term backup during grid failure. So if the grid goes away, the traditional role of UPS has been to provide a bridge between the long-term backup and the grid failure and the grid. The long-term backup being diesel genset. The UPS is back-to-back power converters with some storage. Again, the traditional UPS has only 5 to 10 minutes of storage just to serve as a bridge from grid to long-term backup. And the modern UPS that we'll talk about more today can have long duration storage to meet various grid and load requirements. And finally, at the end, the compute load. So now, once we go from the UPS inside the IT rack, this is how usually the IT rack electrical infrastructure looks like. You have the low voltage three-phase input going into an IT rack, and then the three phases are divided into single phases, and then the power supply units or PSUs, something like this, where they are just similar to very similar to laptop chargers of slightly higher capacity of 3 to 5 kilowatts. They are distributed between three phases. Generally, there are 6 PSUs in one power shelf, so 2 PSUs per phase, as shown over here. And all of them, these power supply units, they take the single phase AC input and produce low voltage DC output. Again, existing latest data centers generally use 48 or 50 volt DC bus, which is basically a DC bus bar at the back of an IT rack. And then we have several blades and then other power electronic converters. So if you think of it, the UPS is the first power electronic converter that is phased by the grid. And it has 3 operation modes. Primarily, there are 2 major operation modes. One is that when the power flows through this back-to-back double conversion converters. So in this case, this rectifier will be at the front end, and it looks very similar to the PV inverters or battery energy storage inverters. They are 2-level 3-phase voltage source converters. So in the double conversion mode, the front-end converter of the UPS is what the grid sees. The second mode that UPS operates to save on losses and to increase efficiency, and which is the bypass mode, where the UPS is bypassed to the semiconductor switches. And in that case, all the IT racks will be directly visible to the grid. So there are 2 types of power converters that can be seen by the grid within data centers. The first is the front end of UPS, when the UPS operates in double conversion mode. And the second is the power supply units like this, the 3 or 5 kilowatts, but hundreds of thousands of them within IT rack. So what factors we need to consider for EMT modeling of data centers? And first is the architecture. What is the power delivery, how the power delivery looks like, whether the data center uses AC UPS or DC UPS, solid state transformer, sidecar, and what are the converters that are used within IT racks? What is the rack bus bar voltage, whether it is a 48 volt rack or the modern plus minus 400 volt rack, 800 volt rack. If the IT rack uses, in addition to power supply unit, some battery backup unit, which is again another shelf within an IT rack, which can be used. If it uses capacitor bank unit for smoothing of the load. So all these architectures, they impact how you are going to develop an EMT model. And the second is, of course, what are the model applications? Whether the application is just to study the impact of load profile, AI load fluctuations on the grid, or you also want to study some small signal stability issues like control interactions, oscillations, weak grid instability, torsional behavior, how would it changing, fluctuating AI load can impact the torsional dynamics of nearby generators. So these are the factors that we need to consider during EMT modeling. So to summarize this part of my presentation, generally 2 types of power electronic converters, they interface with the grid from data centers. The first is AC UPS, and the second is PSU. Now, AC UPS is very similar to inverters that we use in battery energy storage systems and PV power plants. So there is a lot of know-how within the industry on how to model these inverters for IBRs. In fact, modern UPS, modern medium voltage UPS with long duration energy storage, that use the same PCS or inverter products that are used in battery energy storage plants. So modeling of AC UPS is something that power system engineers are well versed with because of our experience with IBRs. And we need to just use this models of IPRs or inverters when the UPS are operated in double conversion mode. But for the existing data centers where we are still not using this medium voltage UPS and where the UPS operates in the bypass mode, the grid sees the power supply units or the IT racks, and that's why we need to develop good models of IT racks. And so that is just one message I wanted to give here. Now, talking about the converter-driven control interactions, in the previous session, I think Eric talked about oscillations that have been experienced within ERCOT from data centers. So where these oscillations come from, and there are two mechanisms. One is the forced oscillations because of AI load fluctuations. The load from these data centers is not constant, but it varies highly dynamically, and it can continuously hammer the grid and create forced oscillations. And second is control interactions or stability issues, just like weak grid instability in IBRs. Going a little bit into the weeds of this, there are two types of control interactions that can happen within data center and the grid. Again, depending on whether the UPS operates in double conversion mode or the bypass mode. In the double conversion mode, shown by this yellow line, the grid interacts directly with the front end converter of UPS. And that's why its modeling becomes important. If the UPS in the data centers during normal operation, if it operates in the bypass mode, then there can be control interactions between IT racks and the grid. And here I'm showing this two different impedances. Basically, whenever you talk about interactions, they are basically interactions between impedances of two subsystems. It can be either impedance of UPS and the grid, or impedance of the IT racks and the building impedance, which of course includes not only the building distribution network, but also the grid beyond the point of interconnection. So coming to the last part of my presentation, I want to talk about an IT rack model that we have been developing at the lab through a DOE-funded project that we are going to release in a couple of months. This EMT PSCAD model of IT rack. The reason we are focusing on this is, as I said, like there are two main power electronic converters in data centers, UPS and PSUs or IT racks. UPS, we know how to model them because they are two-level voltage source converters, very similar to inverters. And that is the reason we are focusing on IT rack and PSUs. The model that we have we can supply the GPU load profile and then see what is the power that the IT rack is consuming. Now the question is, how good is this model? And we are basing it upon reference design from Texas Instruments. The reason being Texas Instruments is a leading provider for many of the semiconductor switches that are used within power supply units. And these PSUs are kind of a consumer products. They are very standardized. They are unlike IBRs where you can have many different types of control systems, control parameters. The PSUs are highly standardized products. The behavior is standardized and they have to meet certain specifications. And that's why there's limited amount of variability on how they behave. And that's why we can use such reference design to develop generic models, which would be good enough. Now there's a question. Just like IBRs, do we want to go towards black box vendor specific models of IT racks and PSUs, or we just use this generic model? I think because the IT racks, they are way down the electrical distribution network, and because they're highly standardized products, I think generic models would be good enough, but that is just my opinion. So the PSU topology or the power supply unit topology that we are using for developing this EMT model, it depends on this single phase bridgeless totem pole PFC. It's the latest and greatest power electronics converter topology that is used in power supply units today for single phase PSUs. Now the tech industry is looking for 3-phase power supply units, and that will of course will have a different topology, but we are still not there yet. And here is the control system. So what this power supply unit does is it takes the single phase low voltage AC input from the IT rack and converts it into medium voltage DC bus level around 400 volts. And then there are other power electronics converters which takes it down to low voltage DC of 50 volt DC. The control system has the DC bus voltage control and the current control. Let me see how I'm doing with time. And this is how the PSCAD model looks like that we have developed at the lab that we are going to release soon. Uh, it's a single PSU. As I said, a typical IT rack will have power shelf with 6 PSUs distributed between 3 phases. So we can use the single PSU model and create a whole IT rack model. And then we can scale this IT rack model to represent a data center. Now, of course, there's a question about, can we just take one IT rack level rated at around 3350 kilowatts and just scale it by multiplying it to represent the whole data center, or we represent a distribution network? So that's a different part of the aggregation that I'm not going to talk about today. Within the PSCAD model, if you can see that there are various colors, green, orange, and pink for different components, and they represent 3 different fidelities of averaging techniques. The green being when you are using the full switching model. These PSUs, because they are low power converters, they operate at very high switching frequency, 150 kilohertz. And for that, if we use a full switching model, the sampling time step would be very less than 1 microsecond for time step, which we cannot use for power system studies. We can do switching average model, which is the second level of averaging, and go up to maybe around 5 or 10 microsecond, but that is still not enough for using these models for power system studies. And that is why we have developed a technique called double averaging model, which retains the dynamics of ITRX only less than, in the frequency range less than 3000 to 5000 hertz, which is good enough for power system studies. And it allows us to go to simulation time step of a couple hundred microseconds. So these are the things that power electronics engineers don't worry about because they are designing the PSUs. But as a power system engineers, we want to capture not only the accuracy or the dynamics of these IT racks, but also make them suitable for using them for power system studies. I'll skip this slide, which is just about how we have developed this double averaging technique. But this is how the response looks like. Switch model, operating at 0.1 microsecond time step, switching average model with time step of 10 microsecond, and then double average model with a time step of 500 microsecond. And as you can see, the improvement from the simulation time. So really this ITRAC model can be used for running various power systems reliability studies for data centers. We can use this ITRAC model for studying control interactions, performing impedance scan studies, just like we do for IBRs, for finding weak grid instabilities and interactions with nearby data centers and inverter-based resources. In the interest of time, I'll skip this couple of slides, but I wanted to keep them here for record. This slide talks about impedance-based specifications developed by Meta to mitigate some of the oscillations that they saw in around 2016, 2017 timeframe. They were more worried about oscillations within data centers, but now because of the size of data centers, we are seeing them on the grid. And we have to develop something similar for grid interconnection. So to summarize, AC UPS are the power electronic converters that are seen by the grid within data center when they operate in double conversion mode. Modern UPS, which are designed to meet grid requirements as well as load requirements, they actually always operate in double conversion mode. And in this case, the modeling challenges are same, if not the same as IBRs. But for the existing data centers where the UPS operates in double conversion mode, we have to go and do modeling of IT racks and all the loads going up to the low voltage level. With that, I'll wrap up my presentation. Thank you, and sorry for going 1 minute over time. Thanks. I'll transition to Brett Ross from PNNL for the next presentation.
Before that, I want to warm up the audience here. You have a panel of experts. They're going to get you to drink from the fire hose for the next 60 minutes. 30 minutes after that is where you get to direct the fire hose back at this panel. And the whole fun here is the importance of the work will be measured by how many people line up behind that. Don't think in their terms of what research they've done. Think in terms of deflecting the fire hose, they're directing at you, and think of, so what? What's the impact you're making? How does it make sense to me? Where can I apply this? Vertiv is sitting here. Vertiv can say, okay, fine. How do I do this with my IBRs? Start thinking. Thanks. Sorry.
Oh, okay, excellent. Hey everyone, my name's Brett Ross. I'm an electrical engineer at Pacific Northwest National Laboratory. I'm the principal investigator of like the DOE project that's supporting NLR and us being here. So thanks y'all for setting this up. Yeah, and for my part, I'm going to talk about more EMT modeling of data centers, more from like a large signal perspective, in terms of fault response and things like that. Thank you, Shahil, for giving very nice like background introduction on how the data centers are laid out, because I'm pretty much going to jump right into the details of what's going on in the different components. So I'll talk for about 15 minutes. I'll spend a couple minutes talking about some EMT modeling resources that are available for you to use and build off of. Then I'll spend about 6 minutes on the fault response work, and then about 6 minutes on studies for impacts to electromechanical generation and some gaps there. So in terms of the library overview, right now online, there's a data center modeling library, DML. It's essentially a collection of open source components in PSCAD. Shahil's library is coming out that's directed more for converter driven stability. These resources mostly have fidelity around fault response, large signal behaviors, things like that. They're mostly average value models. Kind of the intention with these, I don't know if generic EMT models will meet our needs or not, but a lot of people who are being asked to develop EMT models now have never developed them before, for their product. So these are kind of intended to help them get started. Many of y'all might be familiar with this library already or have used it. It came out back in January. The new version is going to come out in July, pending approvals. It's got improvements to existing models, so a lot more flexibility on the different kinds of fault response that you can represent, more sophisticated coordination between energy storage and the UPS and rack level power supply front ends, as well as a number of new components, more sophisticated grid forming controls, which you could use for either energy storage or the front end controls for certain SST designs, more complete cooling models, and then some reciprocating internal combustion engine models as well. We'll also be showing how to line those up with the Phasor model, and then starting to break out the model a little bit more for people who might want to use it, the models for more plant level studies. All right. So briefly, I'm going to go over just sort of some of the most salient characteristics of the fault response of data center power electronics that you'd see in an EMT model. Some of the general principles, most important things that are going on inside the devices, I'm showing here. Some of the most important elements are you have some sort of AC-DC power converter that's connected to some bulk DC link capacitance generally. And then you have some downstream DC load. There might be more DC-DC converters, additional energy storage, things like that. That downstream process has its own fixed power consumption, and the way the power supply balances that power consumption with the input power is by regulating the DC link voltage to a constant value. Reason being that any mismatch between the input power and the output power, is going to come out of the capacitance and the voltage will decrease. So that's the characteristic that drives, for instance, the constant power nature that a lot of these loads have. For instance, you decrease the AC voltage on the input side, the amount of power being consumed by the DC load doesn't change. So the input stage just increases the current to try and support the DC link voltage. Common things that cause tripping on these devices would be, AC overcurrent due to that characteristic. If the power converter doesn't have a current limiter, or DC link voltage fluctuation, and then some will measure AC voltage directly and trip on that. This is one reason why the actual ride through of an individual power supply may not be very consistent from a grid side perspective, because the rate of that capacitor discharge varies with the loading. So if you have a bunch of power supplies with slightly different capacitances, different loading levels, they're all going to drop off at slightly different times. Here's an example fault response for double conversion UPS. I've got one example where it's riding through the fault and remaining connected, and another where it's entering momentary cessation and then ramping back in shortly after. So like Shahil was mentioning, this would be the primary grid interface for a lot of data centers, but there are data centers that don't use double conversion UPS. And so the rack level power supplies play a role there. You might see some variation, but generally these are three-phase power converters, which are not going to draw much negative sequence current during unbalanced conditions. There's a lot of variation right now between different UPS and how close they are to the sort of ceasing and reconnection type behavior that we're talking a lot about in the phasor modeling space. But they generally operate unity power factor over a broad range of disturbances. So I think one of the other things to mention would be the reconnection logic here you see on the bottom right. This is essentially the batteries carrying the load downstream through this entire period. Like I mentioned previously, not all data centers use double conversion UPS. Some do just have a rack level battery backup down at that 48 volt DC bus that Shahil mentioned, or some may not use UPS at all if they have some process that they're willing to take a couple hours of uptime, of downtime a year. So in this case, these are mostly single phase power supplies. So the kind of tripping and fault response you can see for unbalanced faults is significantly different. Here I have an example where an unbalanced fault causes the power supplies on two phases to drop out. In this case, these tripped on AC overcurrent. And then what I have on the right here is showing that basically that reconnection logic. This is another area where developers are still kind of working on implementing this behavior. So you won't necessarily see this fast reconnection in this kind of distributed UPS data center today, but people like via the Open Compute platform are pretty earnestly working on those kinds of features. All right. So I'll go ahead and move on to the electromechanical impacts then. There's obviously a lot of other nuances to the fault modeling. Please, feel free to ask them afterwards or come and find me. We've done more work to look at, how those interact with protection systems and things like that. Happy to share. But for the electromechanical impacts, I did want to touch on, since we focus mostly on power electronics, I did want to talk a little bit about the electromechanical side of things. As many of you all have probably known, heard, or probably presented on, right, the synchronized training techniques have caused some pretty large active power fluctuations. There are software level controls that can help, but, right, they essentially work by burning power at the rack level, and that's power that they'd much rather be used to put more GPUs in and train a larger model. So there's a strong desire for energy storage to deal with these, and of course we need to have specifications for how large it's going to be and size it right to protect the grid without radically oversizing things. In terms of how the generators are being modeled for these studies, a lot of the techniques used for subsynchronous resonance studies, so where you have a multi-mass turbine model, ideally derived from field data or FEM analysis, those things are being used. The data center itself, because the active power consumed by the data center doesn't tend to be strongly affected by large vibrations inside a generator somewhere else, we generally treat the data center as a controlled source, basically a forced oscillation, some active power source where you're playing in some test waveforms that you've got for a site you're studying. I think Parag is going to touch on this later. Most of the frequency content of the actual currents and voltages in these waveforms is pretty close to 60 hertz. So phasor tools work quite well for actually figuring out how far these oscillations propagate to different generators. So the role of EMT here would be more you've honed in on specific generators that you feel are at risk, and then that's where you're diving in a little deeper. And the main thing you're doing in these studies is you have your multi-mass turbine model, you're looking at the torques in the different sections of the turbine, and then you're comparing those to some sort of endurance curves. There's a couple of nuances there. One is that, I put kind of like an exemplar curve up here. The first one is that you're basically hitting the endurance limit because think about a 20 hertz oscillation going on continuously. It takes about a week to accumulate 10 million cycles, which is generally the highest value that the wear curves go up to. So this is, you may as well just take that limit, and it needs to be at least below that. However, because these fatigue curves weren't really developed with that in mind, with this application in mind, and precision up at this upper limit is not, we don't know how good the precision is. There's a little bit of data out there that goes up to maybe 10 to the 9 or 10 to the 10 cycles that suggests the withstands could be a bit lower. So a lot of people conservatively are going to maybe a little less than half of the endurance limit would be kind of a target value. That said, as I kind of hinted from that, right, there's definitely a lot of open questions on the withstands in this space. I've kind of just talked about the applicability of the existing SN curves. Another area where I've at least run into modeling gaps is on the representation of reciprocating engines for these studies, right? For supply chain, as a host of other reasons, right? Data centers are increasingly looking to reciprocating engines for bridging power, things like that. The little data I have suggests that the resonance amplification problems aren't quite as bad with these as with like a turbine, say. Maybe like an amplification factor of 7 or 8 times instead of 30 times, 40. I don't have very much data though. And the other aspect is the actual steady state torque in the reciprocating machines is unsteadier because it's a reciprocating engine and not a turbine. So you have that added source of load on the turbine that you have to account for, or load on the engine that you have to account for. The other one that I'm not too sure about is, right, we have some preliminary oscillation requirements going in for the grid level. And we believe that they probably won't cause any problems for the generators, but a lot of generators aren't fully instrumented with the vibration monitoring. You would need to really know if you're exceeding these, smaller endurance limits, right? If you're, hitting a resonance with, 0.5 per unit torque, you'll probably, everyone in the plant's going to know. But at some of these lower values, I don't think there's actually strong evidence to show that we'll be detecting this damage. And so that's something that I think needs further investigation. That's all I had. If you have more questions, I'd love to talk more. I always say PSCAD is my favorite video game, so I love talking about this stuff. Up next is Dr. Jintan. She'll be talking about some phasor modeling work that her team's done.
Good morning, everyone. So my name is Jing Tan, a principal engineer from the National Laboratory of the Rockies, same place from Shahil. And today I'm going to share very exciting, the latest development of our generic phasor model for the data center. This work has been motivated by the rapid growth of those hyperscale at the AI data center, and also the urgent needs from the utility and the system planners. And this effort actually has been done by the entire NLR team. I'm presenting on behalf of them, including Zaid, Jay, Gapsu, Damjan, Ram, Andy, and Shahil here. All right, so let's get it started. I think the previous speakers, they have set up a really nice stage to talk about why we need modeling. Modeling seems like one of the very important topic we need to tackle currently. And so here I want to keep it simple. And maybe I don't need to talk about the importance of the modeling, but I want to talk about why now. And the left figure actually was showing that you probably can see in the United States alone, there is a rapid increase of the data center electricity demand in the recent years, 23% per year throughout to the 2030, which means 14% of the load demand will be coming from the data center. And then now it's only 3%. So those outstanding numbers make me feel like, wow, there is a huge surge from the data center. We need to think about it. And the red figure actually is showing that the evolution of the data center. So we can see that the data center is not something new. Actually, it has been exist for a long time, but it's evolving through the whole timelines. At the beginning, we have some kilowatts scaled mainframe computers, and then it goes to the couple of the megawatts enterprise IT infrastructures. And then now, currently, today, we are building a lot of kind of like hundreds of megawatts AI training data centers. Then what is the next? For the next, we may reach out to those gigawatt data centers. And meanwhile, we would need to think about why those gigawatts seems dangerous or seems very exciting for us, which is because we probably won't just think about it as a computer or computing infrastructure. We need to think about this probably has the potential to provide a lot of energy support. I would like to treat it as an energy infrastructure in the future. Then the next question would be, maybe you are wondering, we have been developed a load for such a long time. What is existing in the existing software library? And can we just leverage some of them for the data center modeling, just assemble them together? So this figure actually was showing that the evolution of the load modeling in the simulation world. We started with this static load model, and then we added some induction motor models. And back in 1996, after the kind of like famous WAC blackout, and we start to think of the WAC, kind of a lot of utilities in the WAC that are making a lot of efforts to have this composite load model that in order to capture the more accurate load response dynamics. And when we are thinking about the recent year, we also add a lot of good load data there, including the EV model developed by EPRI and the DRA model and a lot of those type of models. Then where is the gap here? So for the data center, so thinking about the future AI data center, it's including a more complicated the compositions, including the cooling system, backup generator UPS, and IT load, plus the more sophisticated control logics there. So this is kind of like bring us the challenges that you need to make sure it can really capture the dynamics of the entire facility. You need to have those things working together and understand those control logics a little bit better. So this is a table that summarizes what's the existing data model availabilities. So here we list the 6 different architectures that has been the representation or representative for the data center architecture from now to the future. So as you can see that we have that crypto mining, which is a very simple architecture without a UPS. And now for the centralized UPS that Shahil presented, and that one actually is a very good representation for the current data center usage. And when we're moving towards to the future, the distributed UPS, SST, low voltage DC distribution, the type of the data center architecture actually will be something under the consideration. So this is the open source model availability so far. I also list the reference here. So fortunately, I feel like the whole community is working so hard on the kind of like a model development. So Brett, PNNL, developed the EMT model for the first 3 architectures, fantastic work. And we have been doing the Phasor-model. So this gives you an overview of the model availability that this community actually can use for the existing study. So we still can tell there is the modeling gap. Before I directly jump into how we do the Phasor model, I think it's very important to understand the physical components within the data center. Shahil already covered a little bit, but here I want to repeat one more time from a system planner modeling perspective, from kind of like top down. So if you are thinking about the power flow, how basically this is a simple question: how do you deliver the electricity to your IT rack? So it starts from the grid side, and the high voltage will goes to the transformer and the switch gear. So this figure I borrow it from the Siemens webpage. So it come from here, and it will go through the step down transformer, and then it will go to the building stage, and it will go through the UPS and the batteries. Within the UPS will support the UPS functions during the disturbances. And then it will go to another stage called the power distribution unit. So this one will help you to distribute those powers, electricities into the individual, the IT rack hall, and then go to those IT servers. And in parallel, you probably also can see that in order to make sure our IT rack can work properly, we still need some services there. One important thing is the cooling system. So it will have the cooling system being included within the data center. And another typical thing is we need to have people to work there. We need to have a lot of additional office load to support the lighting or the monitoring, or including the EMS system. So if we think about what need to be modeled in the Phasor model, there are a couple of the key components that we actually need to be captured. So from the modeling perspective, we need to ask us a question: what should be modeled, and how details those things need to be modeled? So when we translate this power transfer to the one single line here, I think this is help us very significantly to understand at which stage what will be highly aggregated and how detailed we should model it. I think Shahil already put that in a very nice way. I won't repeat it here one more time, but I just want to raise up two things. The first thing is the network within the campus actually need to be considered. So as you can see, from the POI and down to the UPS level, there is the network that we need to model in this one, because when you put the requirement to a POI, it doesn't necessarily mean that's the voltage you have seen in your UPS level. The second thing is I want to emphasize there is a need to fully understand how those components actually is working with each other, interact with each other. The thing is, this is actually the places we will need the inputs from the OEM developer and help us to better understand if there are a better way to modularize these structures. Then we come to the modeling approach. So for the Phasor model, it's very clear that the model needs to be developed to support these transmission planning studies and the interconnection studies. So the key purpose for this model have two folds. One is we try to use it to capture the impact of the grid transit on the data center part. So which means we want to know when we have a fault in the grid, how this data center will perform. First, it will disconnect or still maintain connect. If it still maintain connect, how much support it will be provided during the transit. Second layer is captured impact of AI data center on the grid. So because we just mentioned, there are so many characteristics from the IT load, like the oscillatory characteristics. And you can see when we do the AI training, it will have that ramp up, ramp down issues that are reported by NERC. So those things actually will have a significant impact for our grids. Does our grid can handle it or not? These things need to be captured. Second is this reconnection impact. So as you know, when we are doing the low voltage ride through, so basically the UPS, the first priority is protect the IT load, is not protect your grids. So basically we need to think about doing that reconnection. So how the grid connect those nodes step by step. So those need to be captured. And meanwhile, this data center interaction with other IBRs or with other synchronous generator need to be considered. So some of the dynamic phenomena beyond the phasor domain, like a higher frequency, that probably need to be captured with the EMT model. However, within 10 Hertz, there still could be some interactions. For example, there will be the inter-area oscillations. Originally, this is a synchronous generator issues. However, when you are thinking about the data center, if it can also enforce some oscillatory mode within that frequency, we should capture that in the Phasor-model as well. So with that, I would like to emphasize that we would like to propose a more modular component level modeling framework that can be adopted to enable those independent development, validation, and the future enhancement. Because with this, I would like to make this like a Lego structure. So when you are doing those modeling, like what I'm putting here for the cooling system, for the air cooling or for the liquid cooling, maybe you can use the different model to represent it. We will dig in that later. And for your UPS, this is the most biggest focus right now. You probably can utilize the existing batteries to do a lot of things. Batteries to support things. However, you also can control your batteries to help to mitigate some of the oscillations. So this is totally a control-related strategies that you can put that into your UPS. And not mention those co-locate resources. I put a backup generator here, but do you require it to just reconnect, restart after 15 minutes, or you want to put a large batteries at the medium voltage level and doing any support? So that's why I want to emphasize this modularized structures for the entire Phasor model. It's kind of like very similar to the composite load model kind of a philosophy. However, I think this will be highly helpful for us for the scalabilities in the future. Then I summarize, maybe I shouldn't go to the details for how we develop those Phasor models one by one. I just emphasize when we find out for some of the model, if we have those in the existing library, I don't think we should overcomplicate them. However, for some of the components like the UPS, those are power electrons that will involve the more complicated control logics there. We need to use the UDM, which is the user-defined model to model it. And we also use the UDM trying to capture this mode switch, which is Shahil mentioned that from the double conversion to single conversion bypass mode, how they can operate, shift from one mode to another under which circumstance. And yeah, so let's keep going. I don't have the time to detail the model from the model perspective, but I do want to share even within the UPS model. I just mentioned the UPS is important. We need to modelize it one more time. So this is will provide us the module for rectifier, and it goes to the we call it the battery part. It's through the DC link, and also goes to the voltage source inverters that is performing the power supplies for our downstream IT load. So we could simulate the whole control logics here and make sure how those batteries also can be tested when you have the different control logics, control designs for your rectifier, batteries control, that DC-DC boost, and also this VSM at VSI. So you could have a very different performance for your UPS and try to understand those different, when it's operating at a different operation modes, what's the services or what's the dynamics actually it can provide to your grid. I think I will skip this one. This is just the one page. I want to go over what is the normal mode, which is sometimes we call it a double conversion mode, and the backup mode, and the bypass mode. And let's take a look at the validation part of this proposed Phasor model. So first thing we have done here, after we developed it, we have testing it for a couple of steps. First, we boosted the AI load from 0 to 700 megawatts at 1 second. And then we deploy a grid three-phase fault at the 3.5 seconds. And then we clean it up at the 4 seconds. And then this time period was showing the reconnect of the node. So this looks like a simple simulation happened within 10 seconds. However, this helps us to test out how the UPS is operating from the double conversion mode, and when it sees voltage, actually voltage sag is around 0.4 per unit. It converts to the single conversion mode. The reactive fire goes to the momentary cessation, and the battery start to serve the load automatically. And after that, when we clean the fault, and how this is going back to the double conversion mode, how those batteries support this reconnection, and make sure the blue line actually is how IT rack is saying outside of the power supply. We can see it's still, there is nothing, IT rack actually has been affected during the whole transition. I do want to emphasize one thing, which is this model actually can capture the rapid data center load ramping and its impact. One example, I think you may familiar with this one is in the NERC's report, they mentioned in a very fast ramp period, the demand can change 2 per unit per second for within a really small time period. So this is how we capture it in our simulation. The next one is a model can capture this UPS read-through process. What emphasized here is you can see how the blue line shows us the battery, how it's supporting the IT load, and how the reactive power, active power of the reactive fire actually can gradually drop down. So this dynamics has been captured. One thing I do want to emphasize, so at this stage, right through momentary cessation, there is no additional kind of like needs to see how the POI should see those reactive power. So for this one, is some advanced read-through requirement actually can be added on top of the existing model. The last one, just want to showing you that the right figure is showing in the NERC report showing the oscillations, ramp up, ramp down characteristic, and the left figure is showing our simulation. The last question you probably was wondering how accurate this Phasor model is. So here we put the PSPD model. Okay. PSPD model from PNNL, and it's the dash line. And also we have the solid line, which is the Phasor model's performance. You can see the very good agreement here. So this comes to my summary. We have developed this generic modularized component level data center models that can capture the key UPS operation modes. And at the end, I do want to emphasize one thing. So in our mind, for the future data center, is starting to evolving from just care about themselves, move to the grid caregiver for the data center. But this will require a very advanced considerations from different aspects, including architecture, controls, and grid services designs. So at the end, I would like to give a shout out to the key main contributors here. And I also want to call for the collaborations for our model. So far, we validated this against the EMT model. We also hope we are able to get the owner to validate those models against the real field data. So if you are interested in testing this Phasor model, we are happy for the collaboration. Thank you. I will hand it over to Parag to give his presentation.
Okay. Oh, this is Mike. All right. Good. Great. So what I'm going to talk really about is, again, the Phasor domain and all of these things. But really what I want to focus on is how do you look at models in the context of the challenges that you are trying to study, trying to mitigate, right? So what are the challenges with large loads data centers mostly, and how are they impacting bulk system stability? And that is why we need the models for, right? So if you look at what we know right now, and this comes from multitude of reports that have been published, you might have even seen public reports on news channels right now, but things that we are more interested in, that we are concerned about, the primary one that we have been talking about is loss of data centers, right? Why is it important for the modeling context? Well, if you're a planner, right, you want to study whether these things happen on your system. If it happens, how it impacts your system and what you want to do about it, right? So that is where the modeling piece ties in with the risks that we start seeing with large loads. So unanticipated data center disconnections, it's kind of a big thing. We have to also start thinking about what are the domains, right, the tools that are most suitable to study some of these things. And that kind of gives us an idea of which type of models we want to use, which software we want to fire up if I want to study something like this. These type of things we can study in Phasor domain. There is a lot of benefit in studying these things in Phasor domain because the impacts that you're looking at affect the interconnection, right? So you want to have some place where you can study a large enough model. Phasor domain is that. The next risk that our speakers kind of alluded to and spoke about in a little bit detail is how AI training, the fluctuating load, how they can affect your synchronous machinery on the system. How do you study that? Of course, you need EMT to study it, but screening, right? You want to screen for things before you get into the details, and that is where Phasor domain tools again become beneficial. And I'm going to talk a little bit about that. The last one is something that hasn't been reported a lot, but it's not outside the realm of possibility. This is if you have large inverter-based resources located close to data centers, they have all power electronic equipment, there's a possibility of controller interactions and such. When these things come about, how do you study them? Again, that's more suited in an EMT type of framework. So with this kind of background, let's talk a little bit about how we think about these things, right? And this is a good chart that I sometimes find very useful when I have to talk about things at a very high level, right? So what are the challenges that we're looking at? We have to kind of split it out into frequencies, right? And 10 hertz is very optimistic, might not be 10, might be a little bit less. Take that with a grain of salt here. But if you're looking at slower interactions on the system, you want to study how it affects the broader systems. You want to have a model that is capable of representing the slower dynamics and can capture a wider portion of your system. Phasor domain tools, PSSEs, PSLFs of the world, the power world, the DSA tools, they are much more suited to do this. You want to use these kinds of tools, right? If it's a higher frequency event that is kind of undamped, kind of causes problems, that is where you want to get into EMT because those effects are mostly localized. At least the initial impact is mostly localized. And you want to model things in much more details, right? So you want to include many more things, and EMT is much more suited for it. You want to kind of understand the risk of all these things, right? So if it's a highly damped situation, generally lower risk for the system. If you're looking to prioritize things that you want to analyze, you can deprioritize things that are much well damped, kind of smoothing out. If it's a blip, you want to make sure the blip doesn't push anything beyond maybe its basic insulation level and stuff like that. But if all of those things are there, you can deprioritize it. What you want to really understand are these events that are growing in nature, that are not damped out by any kind of system damping that's available. So again, if I try to place things that we are more interested from the bulk system impact side of things, so the inter-area oscillations, the right-through, et cetera, they kind of fall into this Phasor domain space. Anything that's higher frequencies, SSCIs, subsynchronous controller interactions, torsional interaction, resonances, et cetera, all get into EMT. So with that perspective, let's start talking a little bit about the models that we have today and that we can use and how these models came about, especially for the Phasor domain kind of stuff. Here we spoke about the EMT domain things, right? So a lot of our presenters spoke about what the data center looks like. I won't beat this horse to death, but irrespective of what it is, it's a bunch of electronic equipment that interfaces with the grid. If you pick up a textbook and start looking at what these electronic devices are,
primarily for the front end of these devices, you will see that all of them try to control a DC bus. So essentially what they're trying to do is the front end interfaces with the grid, tries to create a DC bus, which is stable and stiff for the load, right? So if you start approaching modeling from this perspective, right, again, realize that the models that we are developing, it's perfection is the secondary goal. The primary goal is getting something that helps us understand the risks, the opportunities, and helps us make meaningful decisions. So if I've made a decision that made a difference, my model is good enough. So we look at all of these things from that perspective. So it is primarily an electronic load. You have UPSs. You might bypass them and directly connect to the power supply units. You have a bunch of cooling load that are generally behind variable speed drives, again, electronic loads, and then you have a little bit of lighting here and there. So how do you model all of this, right? Jin pointed out, you do need a modular structure to model all of these things. You need to put different components. The composite load model was actually developed with this idea in mind that the time it was developed about 10, 15 years back, we kind of gave people a fixed structure, but now it has changed. It allows you to do modular model development. So moving forward, when you upgrade to new versions, you will see that it allows you to interconnect different components and represent this whole structure. So what is the model that we have today? So the Phasor model that we have today, this is called the PERC-1 model. It's called the Power Electronic Reconnection and Seizing version 1. Very importantly, it says version 1. Why? Because we expect version 2s, 3s, 4s, and all of that, right? That's why we call it version 1. So the model is a performance model. When this model was developed about quite some time back, it was developed from the perspective of a utility engineer, where they would have access to measurement and they would tune a model to meet the measurement. Performance models are best suited to do that, and if you want to have a deeper conversation into that, I can tell you about the advantages of doing that. Won't get into the details of the model, but just to give you a flavor of how this model came into existence, so EPRI was funded by Lawrence Berkeley National Lab back in 2021, and we were primarily looking at electric vehicles, and we came up with this model. Later on, we found that the model could be extended to model a whole bunch of power electronic devices because of the same principle. The front end is trying to create a DC bus, right? So the controllers on the front end generally tend to remain the same. So how did we validate whether this model works well? And I'll show you a few plots to kind of impress that on you. So at EPRI, we do a bunch of lab testing. So we did a lab testing of a bunch of power electronic equipment, EV chargers, we did variable speed drives, we have done UPS systems and all. They give us unit level ideas of what these devices do when you have different type of disturbances impressed on the terminals. That is one piece of the input. Then we also developed EMT models similar to what Shahil and Jane and Brett presented. So those models, they allow us to look at what the facility level performances look like. And the idea was that we come up with a simple model that is targeting only the slower frequency changes that we see out of these type of setups, and try to capture that with the simplest model possible so that it's easier for folks to work with. Try to keep it simple. When you look at the model structure, you see that it has, I don't know, 140-ish parameters. So simple is complex, right? Okay. So just to give you what the capabilities of the Phasor model are, again, won't get into a lot of details. We tested this out. So what we did was we used the Kundur's two-area system, primarily because we also wanted to look at oscillations. We created one in EMT using the full facility EMT model that we have at EPRI, and then we created one in PSLF. And the idea was to get a comparison of the slower responses. We are not really bothered by the fast responses yet because we know we can't capture that in PSLF. So we did a bunch of tests. The first one was what we call small disturbances. So kind of the small signal behavior of the models and see how they compare. You can see the blue and the orange curves. That's the EMT versus positive sequence. You see that there is some mismatches. We do expect that. Again, perfection is not what we were chasing. We want something that we can work with and make decisions. The second one that we looked at was write through. So what happens when you put a disturbance, the model disconnects and it comes up with a certain type of ramp. We programmed the ramp rate same in the model as well as in the EMT model, try to see if there are certain things that show up in the EMT model that we are not capturing. We do see that there is good match there. Again, won't get into a lot of details of this, but again, if you want to have a discussion, there is time to do that. Then we also looked at what is the effect of these things getting connected to the grid and how they affect the inter-area oscillation. So these are primarily the electromechanical modes of oscillations below 2 hertz, right? 2 hertz to 1 would be your local modes, and then you have your inter-area modes. So we kind of looked at different regions where we set up the data center model. So we put it in area 1, area 2, both areas, and try to see what we observe in PSCAD in terms of their effect on damping, positive or negative, for different type of disturbances, and how that compares to when we model this thing using the PERC-1 model in PSLF. And then what we observe is that there are certain situations where these loads can improve the damping. There are certain situations where these loads can degrade the damping of the system. And this is well known. If you look at the Western Interconnect Disturbance Report, which was done, you will see that same conclusions were arrived at. So nothing new over there. But what we wanted to compare between PSCAD and PSLF was, are we getting the same type of damping ratios? Are we getting the same type of effect? And that is what we observed, that the trend of damping is consistent across EMT and the phasor domain tools. So again, gives us some level of confidence that this model can now be used to do a lot of our phasor domain studies for our bulk system. And if you see the NERC level 3 alert, it does point out that you want to use a model that is PERC-1 or better. So, like I said, PERC-1 is not the end all. There's a PERC-2 that's going to come out. And what's going to be the big difference in PERC-2, right? The big difference in PERC-2 is if you look at the write-through requirements right now, these are all multi-point voltage versus time curves. The PERC-1 itself doesn't have the ability to do that. Although you can run a bunch of studies, you can trick the model to do a lot of these things. And again, that's a deeper conversation. But in PERC-2, we want to make it much more standardized. So in the PERC-2 development, a lot of these things are going to show up in the model. You will have the ability to model a lot of these write-through characteristics. If you're a planning engineer and you decide that a data center is going to abide by my write-through interconnections, let me see what is the impact on my system, the model is going to let you do that. And then we're also including a whole bunch of ramp rates here and there with the full understanding that these are power electronic devices. The equipment at the end doesn't really have a lot of inertia, so you can kind of move it up and down with different ramp rates. So things might have different ramp rates, right? So we are going to put that in. And just to give you, based on our experience, what we've learned is typically in phasor models, the most number of things that get added in different versions are ramp rates, limiters, and auxiliary inputs. Anybody who has worked in this space knows that that's what is primarily the changes that keep happening. So last piece over here, the forced oscillations, right? So why are we scared about this? Brett pointed out you can't be perturbing a thing too much. It's not designed to do that. It's going to develop cracks. That's what happens, right? So how do we do these studies right now? You would develop a multi-mass model. You would generally run studies. You would kind of estimate what the air gap torque looks like. You take the torque, you go back to the manufacturer. The manufacturer looks at it and tells you whether it's acceptable or not. That's what happens. The multi-mass models by itself, they are not an exact replication of the generator itself. There are other coupled components as well. The bearings, the turbine, blade, shaft, a whole bunch of things over there. You talk to those guys, they tell you it's much more complicated than what you have in the PSCAD model. That aside, what do you want to do when you're doing these things in phasor domain? You want to limit the amount of perturbation that shows up at the terminal of the generators. Again, this is where the screening part is where phasor domain models can be useful because they can allow you to do a lot of these things in a very short time. So how do you do that? Well, you can put in perturbations in the system. You can push the load up and down, and you can see how much of it shows up at the terminals of the machine. Generally, this works good in phasor domain if you don't have a lot of series compensation on your system, because if it's an impedance, right, it's j omega L, it proportionally goes up and down as the frequency changes. with capacitances, it becomes slightly different. So you could do this if you in phasor domain if you didn't have a lot of capacitor compensated lines. It generally works out. So therefore, we were trying to see if you can do this even in steady state, right? So what if we can do this in steady state without even firing up dynamics? So we have been looking at short circuit-based method. There is some precedence over here. Unit interaction factors kind of went through this approach. There were some limitations. We are testing it out, how good it works for mesh system. We know it works well for radial systems, but we are also testing it out, how good it works for radial system, for mesh systems. But there is, bottom line being that phasor models will provide you opportunities to do some screening. So even for these cases in screening, you can still use it. So last slide here. What is your guidance on data center modeling? Well, the existing phasor models, we recommend them for transmission planning studies right through inter-area oscillations like it showed. Multiple instances of this phasor model, the modular structure is there. You can start using it. You can put multiple instances of the PERC model trying to replicate what your UPSs are doing, your PSUs are doing, your VFDs are doing. And then if you're looking into EMT, before directly jumping into EMT, there is benefit in kind of seeing how these models help you do some screening so that you can target the ones that are most important. With that, I'll stop here, pass it to Rahul, who is going to talk a lot about the usage of these things when he does his studies. So, Rahul.
Okay, good afternoon, everyone. How's the energy in the room? Okay, not bad. Okay, good. Okay, I know that, I'm again, every time, whenever I'm at a conference, I always get picked right before lunch. So I know I'm like in between things, but okay, so I'll try to be efficient here. Now, so one of the things that I wanted to try and do is, we've definitely seen that there's a lot of good progress happening on the modeling side, right? So we are making a lot of progress. We are learning new things, and we're going to go to like from PERC 1 to PERC 50. It's all good, right? But like Parag said, small things will change, but every change is meaningful. And we also have a team that's building really great EMT models for us and trying to open source all of them. And so there's a good level of information exchange that's happening. Now, what I wanted to try and do is from the perspective of the interconnection requirements that we are seeing showing up everywhere, try and talk about how these models are being used, either to verify whether the interconnection requirements hold in the system that you're studying, and also maybe think about how you could use these models for the different studies, right? I know Eric and I have been talking about this for a while. There's a lot of work that's going to happen on what models to use for what studies, but all that is yet to come. Now, with that being said, I think just two questions just to help frame this out, right? So, what is well addressed? So, a lot of good modeling. We've spoken about the CMLD, the composite load models, the modular structure, PERC 1, PERC 2, a lot of user-defined models that we're seeing a lot of folks build. Also, a lot of detailed models for EMT. And now there is a component level taxonomy that is getting more common. We have the UPS, we have the cooling system, the motor load, whether it's VFD connected, motor direct line connected, all of those are basically being built out. And we're also seeing, for example, from there are some level of model verification, validation, big difference that we're seeing show up. Like in ERCOT, they have a model quality test curve that we're seeing people now look to verify right through ability or compliance with. But really the gap appears to more or less be something that Parag hinted at, which is which model, what output, how do you use the model for what study? Now, if we are coming up with requirements, how are we going to verify that the requirements matter? And how do we even know that the requirements are right? Right. And so that's something that I wanted to just talk about. So let's associate like a requirement category with the model type and what the model must really deliver. So with that, just to set the stage again with the architecture that everybody has already discussed to a great level of detail. What I want to say is, again, it's really a requirement being measured at the POI, and all of the behavior is really originating very, very deep into the stack. Right. And so we have the step down transformer, we have our IT load, we have what is UPS, battery backup unit, we have our cooling load. There is a battery involved that sometimes gets used for smoothing. Now, we are looking at a lot of these load profiles, load shapes that are all originating at the hardware level. But as they translate upstream, what you measure at the POI, which is where we are applying these requirements, could look very different, right? And I don't think there is a lot of discussion around that. But of course, I mean, you need to measure it, and that thing is all being built out, and there's a lot of work NRL and all the labs are doing on that front. So that's all great. But I think the requirements are really originating at the POI. And we have the right to requirement. There is this whole discussion around what is constant power behavior, constant current behavior. When you are riding through an event, what kind of behavior do you want the data center to adopt, right? And what behavior can be driven by the existing power electronics, and what is something that you're going to force it to do, right? So those are things that we need to think about. Ramp rate is a concept that applies in different domains and time frames, right? You have a ramp rate that applies on a per minute basis. You have a ramp rate that applies on a 5-second basis, and then you also have this whole discussion around power quality and all, which I don't want to mix. But then you're going to see that I make the mistake of mixing it in a few slides. But anyways, they're all different concepts, different phenomena. And then we have the oscillations, right? The load behavior, PLL dynamics, rectifier impedance. A lot of that is invisible in the phasor domain, which is naturally why we have to transition to EMT. Now, this is kind of the first stab at the mapping, right? So voltage write-through. So like it has been discussed, the phasor models are very useful for this. Some of the dynamics around constant power, constant current that I spoke about before, that could require an EMT model, right? But then I think the use cases of where you need to study that are more limited. I think it goes more into the discussion about validation and all of that, which is more later stage. But from the perspective of arriving at what requirements make sense to you and how to study for it, I think the Phasor models are plenty. Same for frequency write-through as well. Keeping in mind, again, that these write-through settings, the ability for some of these power supply units, UPSs, to write through is there's a wider frequency band, and sometimes you need to think about what your under frequency load sharing set points are. And if you have a generator that's sitting right beside you, when is that generator going to trip? How do you correlate that with your load strip settings? A lot of dynamics in flow, but yeah, phasor models are good for that. Now, post-fault active power recovery, again, that is a very interesting one. And we are seeing a lot of discussion around if you are within the write-through curve, do you reconnect within 1 second? Do you reconnect within 2 seconds? What happens if you fall outside the write-through curve? Does that still count as post-fault active power recovery? Technically, it doesn't, because if you're outside the write-through curve, you've met your obligation, you can disconnect, right? Now, if you have a battery that is going to suddenly show up, right, and the load is still connected, but then the battery is kind of overtaking and showing up as a grid for you, that battery is going to need to perform at a different kind of ramp rate than how you would typically expect a grid connected PSU, which kind of reduces its power output proportional to the voltage to behave. Different considerations, right? And all the NERC papers are going to go into all of that. Spoke about ramp rate again, aggregate impact. From what I'm seeing, a lot of the ramp rate discussions are spreading into 2 different domains. There's one aspect of it that has to do with grid balancing, right? You have regulation reserves, you have area control error, you have AGC set points, you have a certain amount of generation that can respond to the deviations. And you're talking about deviations in terms of the per minute, where you're really talking about a load that's close to 100 megawatts, suddenly wanting to wrap to 150 megawatts, which is basically changing its set point, right? And so that's one way to think about a tier 1 ramp rate. A tier 2 ramp rate is during that period, what exactly are you doing? Are you oscillating and are you moving to the next set point? So that becomes a tier 2 ramp rate, and you see set points like 10 megawatts per 5 seconds, all of those show up, right? So I think that's something to distinguish. And then another aspect of it is, of course, we talk about the oscillations, we talk about power quality. Won't spend time on this because I think everybody's spoken about it a lot, but there are a lot of those studies that become important for the EMT domain. Just keeping a check on time. Okay, voltage write-through. So like we said earlier, phasor is sufficient. So let me say this. So yesterday, CalISO released their large load requirements. If you look at their large load requirements, it looks a little bit different from everybody else's, right? So I think there was a starting point, which was, let's say we start with ERCOT's requirements, then we run our studies and we see if those requirements are good enough, right? And you'll see that in certain bands, like the 0.5 to 0.8 per unit and all of that, they are actually asking for a longer duration for you to be able to write through. Then the question becomes why? Now, what's unique about the grid in the WEC that you don't see a lot of in the East? You have fault-induced delayed voltage recovery. You have a lot of single-phase AC motor load that's stalling. So if you have a deep fault and you have a voltage profile that's recovering, how much of time do you spend in these different voltage bands helps you arrive at a write-through curve, right? So you need studies to be able to tell you that, right? And so that's kind of what I saw as one of the nuances in the Cal ISO requirements. Now, apart from that, everything from the behavior during the write-through curve, we spoke about that, constant current, constant power, the whole 3 strikes counter. There are ways to model all of that. Efficient, maybe not, but gets the job done, definitely. So those are ways to think about it, right? And so what I will say is that a lot of the write-through behavior could be driven by a lot of firmware changes. There's a lot of behavior within the envelope of the write-through curve that you might need an EMT model for. But I do think that when we start getting into more the verification, not validation, then the EMT models start becoming more important. Now, in the interest of time, so protection settings, yeah, this is the frequency write-through. We already spoke about that. I think it's important to be able to correlate your UFLS set points and all of that. Also, the behavior of some of the generator strip settings to how your load is going to behave, especially if it is co-located. We are seeing the impacts of some of that in the system studies. And so you need to be able to override the typical settings of frequency write-through. Just because you do have a wide band to play with because the electronics can withstand it, doesn't mean that that's the band you should play with, right? And that's what studies can tell you, and Phasor models are helpful for that. Post-fault active power recovery, there are a lot of nuances here, which I think only the Phasor modeling, which is good enough, can tell you, right? If there's too fast of a ramp, I know that there is an expectation that as within 1 second or within 2 seconds, we need all the load to reconnect up to 90% pre-fault levels. There are certain systems that can withstand that, and there are certain systems where the more you delay it, the better it is for you. You start looking at seeing some of these dynamics as you get more into system studies, right? And so we see a lot of this in the analysis that we do. And recently, I think the ERCOT requirements had a very interesting edit, right, that showed up, which was, I think if you are going to be going into momentary cessation, which means that you're still grid connected, but your active power reduces to 0, but there is a battery or there is any other kind of transfer that's going to start showing up to the grid as a load, you need to be able to reconnect much sooner. And so the 1 second, 2 second requirement that you had is now reduced to 0.5 seconds. Take a look at NOGA 282 and reach out to Eric. Okay, he's not here. He ran away. Okay, good. So the ramp rate requirements, again, this is the slide where I mixed the two, and there he comes. Okay, so and so over here, the Phasor requirement, I said you can study things. A lot of it is maybe even doesn't need Phasor modeling. There was this unique case where we were looking at the behavior of EB load because they were all supposed to start charging at 1 in the morning, and you could see the impact of that and what that does to the regulating reserves and how you exceed your area control error and you start sending the signals to generators outside your balancing authority to ask them to participate in governor response. There's a lot of stuff that you can glean on through statistics of your existing system operations that you can use to come up with what ramp limits work, but there is also a back calculation from your regulation reserves and all of that. And I think Phasor modeling is pretty good to understand what the impacts of that are going to be. I got 3 minutes, okay. But everything else on the power quality, the flicker, all of that definitely needs EMT, and I'm not going to spend time on that for now. But what I will leave you with is basically there is a 3-tier framework in which I'm looking at these ramp rates. One, of course, is less than X megawatts per minute, right? Think about how your load set points are going to be changing. Another one is what's happening within that minute. That's another rolling window. 10 megawatts, 5 seconds. We're seeing that show up in a lot of places. The tier 3 is really more the oscillation-based limits, right? I do understand that there's a lot of focus on the 10 megawatts per 5 seconds, which basically, in other words, translates to greater than 0.1 hertz frequency, just avoid everything. It doesn't look like that's really going to be very easy to do a lot of times. And so you are going to also need to go into a tier 3, which is basically a study-based limit. So within certain bands of frequencies, avoid these frequencies. A good example is Southern company, LIPA. They've done some good work in this space. And just repeating again that EMT is not optional again for oscillation converter stability, but there is a lot of screening you can do with phasor studies and phasor tools. We are doing that a lot thanks to Parag's help, and Brett and team at PNNL also released tools. I think it was 2 days back, Brett. Yeah, which allow you to do a lot of this. So we should definitely take advantage of that because it all exists, right? And so start bugging Brett with questions. And so that is that. And there's a lot of screening that you can do as well. And I really like what SPP has done because they've taken a lot of those short circuit ratio calculation methodologies and applied them to the data center framework to really see where EMT systems get triggered. Now, whether the SCR of 6 is strong, whether it's medium, all that is kind of open to your grid and the specifics of your grid. Also, how much you want to translate like a multi-in-feed short circuit ratio calculation factor to your system depends on your system. So, definitely tread cautiously. But what I will say is that V-grid interconnection and those stability assessments are very critical. So now just in terms of like the open gaps, right? As I'd say model validation is definitely an unsolved problem, but there are no, equipment level test protocols. One thing very commonly is firmware version updates are solving a lot of things. I think Eric pointed to that as well. Hardware improvements at the server rack level are solving a lot of things. And so what you are really trying to plan and design for, you need to have conversations to understand where that whole industry is moving. We are hearing a lot about, for example, at the server hardware level, how much you size the cap banks for. That helps a lot with basically being able to mitigate or manage a lot of the high frequency oscillations, manage a lot of the write through events. So you might not really need another solution, but we need to see where the technology evolves to, right? And like I said, PERC-1 is a great starting point. We've been using it a lot to model not just the traditional kind of double conversion UPS kind of behavior, but also the ones that have the power supply units and battery backup units, what you want to call the open compute architecture. What you want to study in terms of impacts on the grid, that model allows you to do, right? And it is evolving to have multiple voltage set points and all of that. But what do you do if you don't have all the set points? Assume the worst and study it, right? You find a problem, then start seeing how much you need to really start focusing on it. One key area is really the aggregate behavior. That is something that I think there is not a lot of experience with yet. Whether you're aggregating at a building level of a large data center facility, or whether you're aggregating in, let's say, the entire Northern Virginia across all the data centers, very, very different, right? And the impact of all of that is not well understood, but can still be studied. And, I don't think we can model entire Northern Virginia and EMT yet, but then at least the Phasor models are great for that. So last conclusions, requirement categories, model fidelity, we spoke about that. Voltage write-through, frequency write-through, transient stability, all of those are great in the Phasor domain. Model validation remains the unsolved problem. Phasor models, I think the CPL instability is an issue. So ask yourself that question, is that something you need to really worry about? Then maybe think about even some of the things you do in Phasor, moving them into EMT. And I will leave you with that. Back to you, Ashok. Yes, sir. Thank you.